Hey everyone, hello and welcome. So here we're talking about exponential functions. Previously we've talked about linear functions, which allowed us to study quantities growing at a constant rate, right? The rate at which they're growing at, that was the slope. The slope was constant at all points along a straight line. So you think of the slope, the interpretation being the effect of a 1 unit increase in the independent variable, or the x variable, on the dependent variable, the y variable. Well, now we're going to talk about what happens when we have quantities growing by a constant positive factor, what we'll call the growth factor. These are going to be what we'll discover are exponential functions. So here's our definition. A quantity q is an exponential function of t if it can be written as q as a function of t is equal to some a constant, times some b, a constant, raised to the tth power. B has to be positive. We define a to be our initial value. Think of why that's the case. When we're starting off, we're at t naught, so f of 0 is going to be a times b to the 0, or a times 1, or just a. So that's our initial value. And then b is our growth factor, right? So suppose we're 1 period into the future, then we'll have a times b to the first. It's just a times b, right? This is the growth factor. That's the amount that we're multiplying by a. Suppose we're 2 periods into the future, we'll have a times b to the second. So we have a times b, right? Because remember, the algebraic expansion of b to the t is just b times b times b. B times itself t times. And then lastly, the domain for the exponential function, just a set of all real numbers. So this is the domain is where our independent variable lives, where our input lives. So we're saying that this will admit all real numbers into our t, right? So we can have t can be negative, t can be 0, or t can be positive. We've already seen what happens when t is 0. We know what happens when t is positive. I gave you some examples. What if t is negative? We'll think about that. We'll come back to it. Think about the interpretation of a negative exponent. Okay. So continuing on, a quantity q is an exponential function of t if it can be written as q is equal to f of t equals a times b to the t. This is our definition from the previous page. We have our initial value, we have our growth factor. Now let's talk about this a little bit more. We have a comment about the base b. It's restricted to being positive values, right? Base b has to be positive. Why is that important? Well, if b were 0 or negative, we can get into some problems where b of t is not defined for some exponents t. So for instance, negative 2 to the 1/2 power. And the first time you look at that, that might not look terrible, right? But realize what this fractional power is telling us. This is minus 2. This is a square root of minus 2, right? Raising to the 1/2 power is the same as taking the square root. This is minus 2 to the square root, or square root of the minus 2. You can't do that, right? You can't take a square root of a negative number. It's not defined. Also, what's the problem here? 0 to the minus 1. What's 0 minus 1? Oh, right, so this negative exponent means we move this value into the denominator and change the exponent to be positive. So this is 1 over 0 to the 1, right? Well, that's a problem because you can't have 1 over 0, right? So that's the problem here. So this is the square root of a negative number problem, and this is the divide by 0 problem. And to avoid both of these, we're just going to require that b is always positive. Okay, so you probably knew that already. Here we're just formalizing this with an example, and then with this explanation. Okay, so some examples. For a function to be an exponential function, the variable must appear in the exponent. So just thinking about the class of functions that we're considering to be exponential functions, notice in all these 3 cases, or in the first 3 cases, first 2 of the 3 cases, we have the exponent is where our variable is located. What's in this one? Well, here our variable is in the base. Right? So 27 times 2 to the x is an exponential function. Its initial value, the a, is 27. Our b, our base, is 2. The growth factor is 2. In this case, our a is 120. Our growth factor, or b, is 1.03. Right? We'll see that this is going to be like a growth factor of 3% later on. And then what's going on here? This is 10 times x squared. It's not exponential. This is a power function, right? Here the variable is in the base, right? This is very much like what we've been working on before. This is the first part of a quadratic. Matter of fact, this is a quadratic function. If you think about standard form for a quadratic function, you have ax squared plus bx plus c. Right? This is a quadratic function where b is 0 and c is 0, because the linear and the constant term drop out and we're just left with the exponent term. Okay, so this is not an exponential function, but the first two are. Okay. All right, so let's explore this a little bit more. Where does the initial value come from? So I said this on a couple slides ago, but let's walk through this with a numeric example. Where does the initial value come from? It arises from when the variable is equal to 0, right? So this is our initial period, x equals 0, our starting point. We have q is equal to 27 times 2 raised to the 0th power. Well, anything to the 0 is 1, so we have 27 times 1, or q is equal to 27. So this indeed is our initial value. When x is equal to 0, q is equal to 27. Okay, so now let's think about some modeling, right? So we care about the interpretation for a lot of the problems we're working on. Let's see if we can facilitate that with some of these examples. So the number of animals, n, in a population is initially 500. The size of the population increases by a factor of 1.20, a 20% growth rate each year. So think about how we can write this with an exponential. And what about this one? The price P of an item is initially $25. It increases by a factor of 1.045, or 4.5% growth each year, right? Think about that in comparison to inflation. Inflation, the Federal Reserve targets inflation at about 2% per year. Okay. So stop the video, run ahead and work through these, and then we'll take a look. All right, so now resuming, here is how we'd model these situations using an exponential function, right? So n is equal to 500 times 1.20 raised to the tth power, right? Maybe you used x here, right? So n is our output, 500 is our initial value, 1.20 is our growth factor raised to our variable. Okay, what about this one? P is equal to our initial value times our b, our base is this 1.045 raised to the t. Hopefully use t here because we're thinking about year, and when we think of year or time, we usually use t for time. Maybe you wrote down x. So since that wasn't defined as one or the other, then this would be okay, but in general, you want to pay attention to any variable definitions we might have gotten from the passage. So for instance, we definitely want our output here to be n. Don't say the output's y. Definitely want this output to be p. Don't say that output's y. Right, use the variables that we have in the exercise. Okay, so a couple more examples. So the following exponential functions describe different quantities. What do they tell us about how the quantities are growing? So here's the first one. Number of bacteria in millions in a sample after t years is given by n equals 25 times 2 to the t. Let's try to interpret this. Right, what does this tell us about how the quantities are growing? Okay, then the balance in dollars in a bank account after t years is given by b is equal to 1,200 times 1.033 raised to the t. Is this a good growth rate for a bank account? And then the value of commercial property in millions of dollars after t years is given by v is equal to 22.1 times 1.041 raised to the tth power. Okay, so stop the video, write down your interpretation about the growth of the quantities, and then we'll resume. So what's the interpretation here? This says initially there's 25 million bacteria, and the number is going to double every hour. Double every hour, where's that coming from? Well, hours are entering through this t. So the first hour, right, we go from 25 times 2 to the 1, 25 times 2, 50, oh, that doubled, right? Then try for 25 times 2 to the 4th. Oh, well, or 2 to the 2nd, 25 times 2 to the 2nd for the second period. 2 to the 2nd is 4 times 25 is 100. So we doubled going from period 1 to period 2. And of course, we're going to have this constant doubling. And the same thing is true down here. So the initial balance is 1,200. Balance increases by a factor of 1.033 per year. Right? So every Every time we increase a year, we increase this exponent. And what that means is we're going to multiply whatever is this product by another instantiation of 1.033, right? Remember the interpretation of the exponent. Suppose this is 2. This just means 1200 times 1.033 times 1.033. Suppose this was 3. This is 1200 times this thing multiplied by itself 3 times. Right? 1.33 to the tth power means we have a product of t instantiations of 1.033. And then lastly, the initial factor is 22.1 million. Right? We're told this is in millions of dollars. Right? The initial value is in millions of dollars, and the value increases by a factor of 4.1% every year. All right, so far we've considered increasing exponential functions. They can also decrease, right? And then we have an example of decay. So, for example, suppose we have bleach applied to a population of bacteria. The population begins to decrease, and we have the number remaining after t minutes is given by this function, g of t is equal to 800 times 3/4 to the t. We want to find the amount of bacteria after 0, 1, 2 minutes. I don't know about the scientific basis of this particular example. It seems like my prior is that maybe bleach would be a little bit more fast acting, but makes for an interesting example. And if you're interested, you could probably research and find out more about how effective or how quickly bleach is going to take care of a bacterial situation. All right, so here's the example. We have g of t is equal to 800 times 3/4 to the t. We're going to find the bacteria at 0, 1, and 2 minutes. All we have to do is we just evaluate. So plug in 0 for t. Evaluate, well, we know that's going to be 800 because our initial value is 800 and 0 is our starting point. So we probably know that one immediately. After 1 minute, well, this is going to be 800 times 3/4, so that's 600. And after 2 minutes, that's 800 times 3/4 times 3/4 again. Right? 800 times 3/4 squared, or 450. Right? The constant 800 tells us the initial size of the population. The constant 3/4 tells us that each minute the population is 3/4 as large as it was a minute ago. Right? So this is our rate of decay. Sometimes we want to think about growth in terms of percentage rate, and exponential functions help us here. Matter of fact, in some of these examples, I've been quoting the result in terms of a percentage. So let's think about this. Growth at a constant percentage rate is the same as growth by a constant factor. Quantity that grows at a constant percentage rate defines an exponential function, not and. So here's an example. A person invests $500 in year t, 0, and earns 10% interest. Find the balance after 10 years and after t years. So stop the video and go ahead and work on this. Probably what you're going to want to do is you're going to start from the first period. Start when t is 0, then t is 1, t2. Pretty soon you'll see the pattern. You'll be able to use that pattern to generate your result for 10 years and then for t years. Okay, so now resuming, here's this buildup. We have an initial amount of 500, so as you suspect, that's our A. Well, we have 10% interest. This is going to generate our B term to figure out exactly how we're going to make use of that, and then here's our T. Okay, so after year 1, what's our balance? Well, it's the original deposit plus the interest. What does the interest look like here? Well, it's 500 plus 10% of 500. Right? Earns 10% interest each year. So we start with 500. In the first year, we're going to earn 10% interest on this 500. Right? Well, what I did here is I wrote this out, 500, our initial deposit, plus 10% times 500, and I decided to factor out a 500. Right? And that left me with 1 plus 0.1, or 1.1. So 500 times 1.1 is 550. Right? Alternatively, maybe you already knew, if we want to increase by 10%, we'll multiply by 1.1. That's exactly what we're doing here. Okay. What about after 2 years? Well, we're going to multiply, we're going to have our balance after 2 years is going to be our 550, right? This is at the end of year 1, we have 550. Now we're earning interest on this entire sum, right? So this times 110. So I said we can unpack this given where the 550 came from on the previous slide. So what we really have when we say we have after 2 years, we have 550 times 1.1. What we actually have is, well, we've got our 500 times 1.1 from the preceding slide times another 1.1, because we have the second year's worth. So this is 500 times 1.1 times 1.1, or 500 times 1.1 squared. And now you see this sort of exponential developing, right? Remember, this is taking the place of our variable. And this is $605. Well, the balance after 10 years, you might guess, is going to be 550 times 1.1 times itself 10 times, or 550 times, well, 500 times 1.1 to the 10th. This should be 500. Sorry about that. So let's just make a correction right here. This is not 550. This is 500. Right? This is 500 because our initial A is 500. So must have made a mistake when I was copying from the previous slide. Yep. Anyway, so this comes out to $1,296.87. I'm pretty sure this is correct. You can check that with your calculator. 500 times 1.1 to the 10th. And then this pattern generalizes to the end of t years. So balance after t years, it's not 550, it's 500 times 1.1 to the t. So sorry about that. See this? This should be 500. This should also be 500. The preceding slide is okay. All right, so then comment, we can convert between growth rates and growth factors. So in the exponential function, f of t is equal to a times b to the t. The growth factor is b, given by b is equal to 1 plus r. So in the preceding example, r was 10%, so we had b is equal to 1 plus, well, 0.1. What am I doing? I forgot my warning. So skip ahead. Remember to write r as a decimal. So if r is 100%, we have r is equal to 1. If r is 50%, use r is equal to 0.5, and so on. So if r is 10, if r is 10%, then what I write is 0.1 here. So 1 plus 0.1, and that's what we did on this preceding example, right? Remember, our growth rate was 10% interest, so our growth factor was 1.1. Suppose instead we had r is equal to 9, right? 9% growth. Now we're going to have b plus 1 plus r, or 1 plus 9%, or 1 plus 0.009, or 1.09. Okay. And this is the growth rate. So we have a growth rate. Okay, so in these particular examples, let's try the growth rate and the growth factor b for the following quantities. So the size of the population grows by 0.022% each year. Yeah, this one's tricky, so be careful about this so you're not off by a factor of 100. The value of an investment grows by 11.33%, and the area of a lake decreases by 7.4% each year. So stop the video, go ahead, give it a try. All right, now resuming, the size of the population grows by 0.22% each year. So r is 0.22%, but remember that we got to write this as a decimal, so it's 0.0022. Right, it's 0.22%. So so smaller. It's not 22%. It's not 2.2%. It's 0.022%, or 0.22%. Okay, and then b is equal to 1 plus r, so we have 1.0022. So suppose we have this next one, value of an investment grows by 11.3% each year. R is 11.3. So we'll convert this to a decimal, 0.0 or 0.113. So B plus R, 1.113. What about the area of the lake decreasing by 7.4% each year? Okay, so R is negative for 1. So we write this as negative 0.074 plus 1 takes us to 0.926. Right, so notice this is something less than 1, so we are decreasing. We're not increasing. Notice this was bigger than 1. This is bigger than 1. These are increases. Here we have a decrease. This is less than 1. So when the growth rate is negative, alternatively, we can express this as a decay rate. So whereas we could say it has a growth rate of 0.92, 0.93%, or no, not percent, 0.93, we could equivalently say the area of the lake has a decay rate of 7.4%. In either way, we know the interpretation is that we are decreasing, we are shrinking. Okay, so the last skill that we need for this aspect for the exam is being able to recognize exponential growth from the table of data. So we did this with linear functions. We had a data and actually did two things. One, you looked at a table and you had to determine if one row could be represented as a function of the other row. So you're essentially checking the vertical line test in those examples. Another exercise we had with tables is you had to look and see if you could represent it by a linear function. If you want to check to see if you can represent the data by a linear function, you want to make sure that the average rate of change between any 2 points is the same, right? We're looking for the constant slope. Well, we're doing something similar but different in this case. We want to figure out if we can represent these data with an exponential function. So could the data give points on the graph of an exponential function of the form y equals a times b to the x? If so, find a and b. All right, so what do we do here? It's not calculating slopes, right? That's not what we have with, that's not going to help us here. Because if we're just calculating slopes, well, what we're going to find if we have an exponential function is that we're not going to have the same slope between any 2 points. But that's not going to help us definitively say that we have an exponential function. It's just going to tell us that we do not have a linear function. We actually need to do something else. What is that something else? Well, it turns out we have to try the ratios of successive terms. So this means I divide 5 by 4. I want to see what's happening to my output, right? I want to see what's happening to my output. Is my growth, how's my growth progressing? So 5 divided by 4 is, 1.25. Then I take 6.25 divided by 5, and that's also 1.25. And then I divide this 7.8125 by 6.25, and that is also 1.25. And what this tells us is that the value of y is increasing by a factor of 1.25 each time x increases by 1. That's exactly what we mean by an exponential function. There's an exponential function with a growth factor of b equals 1.25. Can we write down a function? Well, of course we can. We have our initial value, right? When x is 0, x is our exponent. When x is 0, y is 4. That tells us a must be 4. So the starting value is a is equal to 4, so we can write y is equal to 4 times 1.25 to the x to represent this thing here. Okay, very good. So let me know if you have questions.